Let's talk about designing a production-grade URL shortener. Here are the few characteristics that make URL shorteners interesting from a system design perspective. First, the workload is extremely read-heavy. For every URL we create, we might serve hundreds or thousands of redirects. Second, latency matters. When someone clicks a short link, they expect to reach their destination almost instantly. Third, availability is critical. If our redirect service goes down, every short link we have ever created stops working. And fourth, we cannot lose data. Once we create a URL mapping, it needs to stay valid for as long as we have promised to our customers. Let's talk about the functional requirements for our URL shortener. Before we design anything, we need to understand what our system should actually do. The core operations are pretty straightforward. First, we need to generate a unique short URL for a long URL. Second, we need to redirect that short URL back to the original long URL. Third, we should support custom aliases so that the users can choose their own short URLs when available. And fourth, we should allow users to set expiration times for their own short URLs. Beyond these core operations, we need several user-facing features. We should be able to track click counts and basic analytics so that the users should know how their links are performing. We should allow users to update or delete the URLs. We need to be able to support both anonymous users who just want a quick short link and authenticated users who want to manage their URLs over time. And we should also provide an API for the programmatic access so that the developers can integrate our service into their applications. Now that's an important design decision here that we should think about while designing this. The same long URL can produce different short URLs each time it's submitted. This is intentional by design. If two different users shorten the same URL, they each get their own unique short URL with its own unique separate analytics. Our short URLs should be human readable so that using, for example, alphanumeric characters that are easy to copy and share. We need to handle malformed or malicious URLs gracefully, either rejecting them or flagging them for review. And we should support bulk URL shortening for users who need to create many short URLs at once. The key insight here is that the functional requirements drive our API design and data model. Every feature we commit to support here will add complexity down the system, so we should definitely focus our energy and time here. Now let's talk about non-functional requirements. These define how well our system should perform, not what it does. For performance targets, our read latency should be under 10 milliseconds at the 99th percentile. When someone clicks a short link, they should be redirected almost instantly. Write latency can be a bit more relaxed, under 50 milliseconds at the 99th percentile. Creating a new short URL doesn't need to be as fast as redirecting. Our read to write ratio should be 100 to 1 or higher. This is typical for URL shorteners because URLs are created once but clicked many times. And we need to handle millions of redirects daily at scale. For availability and durability, we should target 99.9% uptime for the redirect service. That translates to about 8.7 hours of downtime allowed per year, which is still significant when you think about it. We need zero data loss for our URL mappings. If someone creates a short URL, it needs to work as long as we have promised them to. We should design for a graceful degradation during outages so that the partial failures don't take down the entire system. And we need geographic redundancy for disaster recovery as well. For scalability constraints, our system should be able to support billions of URL mappings over time. We need to handle traffic spikes from viral content without failing over. The architecture should be able to scale horizontally without requiring a complete redesign, and we should plan for the storage growth in terabytes per year. The key insight here is that non-functional requirements drive our architectural decisions. The 100 to 1 read ratio tells us that we need aggressive caching. The low latency requirements tells us that we cannot do complex processing on the redirect path. These constraints shape everything that follows after them. Now let's talk about capacity estimation. Before we can design our infrastructure, we need to be able to understand the scale we are building for. So why does estimation matter? First, it drives our database and storage decisions. We need to know how much data we will be storing to choose the right database and provision the right amount of storage. Second, it informs the caching layer sizing. We need to know our working set size to size our caches appropriately. Third, it determines our infrastructure budget. Capacity planning directly translates to cost. And fourth, it helps us identify bottlenecks before they occur. If we know our expected traffic, we can design around the constraints. Our estimation framework should follow a logical sequence. We start with monthly or daily active operations, meaning how many URLs are created and how many redirects are served. Then we calculate the impact of a read to write ratio. Then we project storage needs over the system's expected lifetime. And finally, we add overhead for replication and indexes. Before we can estimate, we need to clarify some key variables with the interviewer or stakeholders. So, what is the expected URL creation rate? What is the average URL lifetime before expiration? And more questions like, for example, what is the geographic distribution of the traffic? And what is the peak to average traffic ratio? The key insight here is that capacity estimation is not about getting exact numbers, it's about understanding the order of magnitude and identifying which resources will be our bottlenecks. Let's talk about traffic estimation. We need to be able to understand both our write traffic and our read traffic. For write traffic analysis, we start by estimating new URLs created per time period. Let's say we expect 100 million new URLs per month. We should consider the split between authenticated and anonymous users because that affects our data model. We need to factor in bulk operations from API users who might create thousands of URLs in a single request. And we should account for retries and duplicate requests. For read traffic analysis, we apply a read to write ratio to get redirects. If we have 100 million URL creations per month and a 100 to 1 ratio, that's 10 billion redirects per month. We calculate requests per second by dividing the number of seconds in a month, which gives us roughly 4,000 redirects per second on average. We need to identify peak hours and seasonal patterns because the traffic over here is not uniform. And we should plan for viral content which can spike traffic by, let's say, 5 times or more. For growth projections, we estimate year over year traffic growth. We should plan capacity for 2 to 3 years ahead to avoid constant re-architecture. And we need to build in headroom for unexpected spikes as well. And we should also be considering market expansion scenarios. The flow works like this. We start with 100 million URLs per month. That translates to roughly 40 writes per second on average. And we apply our 100 to 1 read ratio to get 4,000 reads per second. And at peak times with the 5x multiplier, we should be able to plan 20,000 reads per second. Let's talk about storage estimation. We need to understand how much data we are storing per record and how that scales over time. For per record storage, our short URL key should be typically between 7 to 10 characters. The long URL can be up to 2048 characters, though the average is usually much shorter. We also store metadata including timestamps, user ID, and expiration time. Total per mapping should be roughly 500 to 1000 bytes depending on our exact schema. For database storage, we multiply the record size by the total URL count. If we are storing 100 million URLs per month at 500 bytes each, that's 50 gigabytes per month. We need to add overhead for indexes and B trees, which can be pretty significant. And we need to account for replication factor. With 3x replication, our storage triples, and we should include tombstones for soft deleted records if we support URL deletion. For cache storage, we estimate that percentage of data is hot data that gets accessed pretty frequently. Most URL shorteners follow a power law distribution where a small percentage of URLs get the majority of traffic. We size our cache to achieve a target hit ratio, which is typically 90% or higher. We need to plan for key and value overhead in our cache, and we should consider multiple cache tiers with different characteristics. The flow works like this. Each URL record is about 500 bytes. At 100 million URLs per month, that's 50 gigabytes per month. Over 5 years, that accumulates to about 3 terabytes. With indexes and replication, we should plan for roughly 9 terabytes of total storage. Let's talk about bandwidth estimation. We need to understand both our incoming request bandwidth and our outgoing response bandwidth. For request bandwidth, incoming redirect requests are small because they just get requests with a short URL path. URL creation requests are larger because they include the long URL in the request body. API requests may include authentication headers that add to the payload. We calculate bytes per second by multiplying the average request size by request per second. For response bandwidth, redirect responses are HTTP 301 or 302 status codes with a location header containing the long URL. These are relatively small, typically around 200 bytes. Error responses for invalid or expired URLs are also small. Analytic API responses can be larger when returning detailed statistics. For network planning, we aggregate both ingress and egress bandwidth. We need to plan for geographic distribution costs because bandwidth pricing varies by region. We should consider what percentage of traffic a CDN can offload from our origin servers, and we need to size the network interfaces appropriately. The flow works like this. Request average about 500 bytes, response average about 200 bytes. At 4000 requests per second, that's about 2.8 megabytes per second of combined bandwidth. At peak with 5x traffic, we should plan for about 14 megabytes per second. Let's talk about API design. A well-designed API makes a service easy to use and integrate. For the URL creation endpoint, we should use a post method with a long URL in the request body. We include an optional custom alias parameter for users who want a specific short URL. We include an optional expiration timestamp for URLs that should expire. And we return the short URL along with the metadata like creation time and expiration time. For the URL redirect endpoint, we use a get method with the short URL as a path parameter. We return either a 301 or 302 redirect response with the location header set to the original long URL. We log analytics asynchronously so we don't slow down the redirect, and we handle not found and expired cases with appropriate error responses. For management endpoints, we provide a get endpoint to retrieve a URL metadata and statistics. We provide a put endpoint for updating expiration time or destination URL. We provide a delete endpoint for removing URL mappings, and we provide batch endpoints for bulk operations as well. The flow works like this. A client sends a post request with a long URL. A service creates a short URL and returns it. Later, when someone accesses that short URL with a GET request, we return a 302 redirect to the original destination. And if the client wants analytics, then they can fetch statistics through a separate GET request. Let's talk about the details of our API design, including validation, response format, and versioning. For request validation, we validate URL format and protocol to ensure we are receiving valid URLs. We check URL length against a maximum to prevent abuse. We verify custom alias format and length to ensure that we meet our requirements. And we sanitize the input to prevent injection attacks. For response format, we should use a consistent JSON structure across all endpoints. We include relevant HTTP status codes to indicate success or failure. We provide meaningful error messages that help developers debug issues. And we return rate limit errors so that the clients know their current quota. For versioning strategy, we should include the version in the URL path like /v1/shorten. We should support multiple versions simultaneously during migration periods. We need a deprecation policy with a clear timeline for sunsetting older versions, and we should prefer backward compatible changes when possible to avoid breaking existing clients. The flow works like this. A request comes in, we validate the URL format, then we check the length, then we sanitize the input, then we process the request, and finally we return a JSON response with appropriate status codes. Let's talk about database schema design. Our schema needs to support all our functional requirements efficiently. For the URL mapping table, the short URL should be a primary key because that's our main lookup pattern. The long URL is stored as a text field. We include a creation timestamp for auditing and analytics, and we include an expiration timestamp that can be null for URLs that never expire. For user association, we will include a user ID foreign key that can be null to support anonymous URL creation. This allows us to build user dashboard features showing all URLs created by a specific user. It enables access control policies so that the users can only modify their own URLs, and it supports account deletion workflows where we might need to find all URLs created by a user. For metadata fields, we include a click count for basic analytics without needing a separate analytics table. We track the last access timestamp to identify stale URLs. We include a custom alias flag to indicate whether the short URL was user chosen or system generated. And we include a status field for soft deletes so we can recover the accidentally deleted URLs. The key insight here is that our schema should be optimized for a primary access pattern, which is looking up a long URL by a short URL. Secondary access patterns like listing all URLs for a user are less frequent and can tolerate slower performance. Let's talk about URL generation strategies. This is one of the most important design decisions in a URL shortener. The first approach is random generation. We generate a random alphanumeric string, check the database for collisions, and retry with a new random string if there is a collision. The approach is pretty simple to implement, but the collision probability increases as the database grows. With enough URLs, we need multiple retries to find an available key. The second approach is hashing. We hash the long URL with the MD5 or SHA-256 and take the first 10 characters. This produces deterministic output for the same input, which can be useful for deduplication, but collision handling is still required because different long URLs can hash to the same short prefix. The third approach is counter-based. We use an incrementing counter and convert into a base62 encoding. This guarantees uniqueness without any collision checks, but it requires distributed counter coordination, which introduces its own complexity. The decision framework works like this, and if we need a predictable output for the same URL, we should use hashing. If we can avoid global coordination, hashing or random generation will work well. If we need guaranteed uniqueness without collision checks, counter-based is the way to go. The key insight here is that there is no perfect approach. Each strategy has trade-offs between simplicity, performance, and coordination requirements. Let's talk about Base62 encoding, which is how we convert numeric IDs into short alphanumeric strings. For the characteristics, we use 26 lowercase letters from A to Z, 26 uppercase characters from A to Z, and 10 digits from 0 to 9. This gives us a 62 characters total, and hence the name Base62. For length calculation, 6 characters gives us the 62 to the power of 6, which is about 56 billion combinations. 7 characters gives us 3.5 trillion combinations, and 8 characters gives us about 218 trillion combinations. We choose our length based on how many URLs we expect to create over the system's lifetime. For the encoding process, we convert the numeric ID to a Base62 string by repeatedly dividing by 62 and mapping each remainder to our character set. We reverse the string to get the correct order, and we pad with the leading character if we needed to maintain a consistent length. The flow works like this. We start with a counter ID, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. We repeatedly divide by 62. We map each remainder to a character set, and we get a short URL like 8, capital M, 0, lowercase k, and uppercase x. The key insight here is that Base62 is just a number system. We are converting base 10 numbers to Base62 numbers using a character set that's a URL safe and human readable. Let's talk about the key generation service. This component is responsible for generating unique short URL keys at scale. The first approach is centralized counter. A single service manages a global counter and increments it atomically for each request. This is simple, but it becomes a bottleneck at high scale. If every URL creation needs to talk to a single counter service, that service becomes a single point of failure and a performance bottleneck. The second approach is range-based allocation. We allocate counter ranges to application servers. Each server manages its own range independently. When a server exhausts a range, it requests a new one. This elimination eliminates the coordination on every single request. The third approach is pre-generated keys. A background server generates keys ahead of the time and stores them in a separate table. Application servers claim keys in batches. This handles traffic spikes without generation delay because keys are already available. The flow works like this. Our key generation service allocates range 1 through 1 million to server 1, range 1 million through 2 million to server 2, and range 2 million through 3 million to server 3. Each server can generate keys independently within its range, and no coordination is required per request. The key insight here is that we are trading coordination frequency for range management complexity. Instead of coordinating on every request, we coordinate once per range allocation. Let's talk about collision handling. Even with good key generation, we need to handle the case where two URLs might end up with the same short key. For detection methods, we can check the database before insert. This adds latency but catches collisions before they cause problems. We can use unique constraint violations in the databases to detect collisions at insert time. We can use a Bloom filter for fast negative checks. A Bloom filter tells us if the key definitely exists or not, which can save database lookups. And we can cache recent keys for quick lookups as well. For resolution strategies, we can append a random suffix and retry. We can increment a counter and regenerate the key. We can use a secondary hash function, or we can fall back to a pre-generated key pool if all else fails. For prevention approaches, we can use a longer key length than the minimum required. More characters means more combinations and fewer collisions. We can implement a proper key generation service with range allocation. We can reserve ranges per application instance, and we should avoid pure random generation at scale because collision probability increases with database size. The flow works like this. We generate a key, we check if it exists in the database or cache. If it doesn't exist, we insert the URL. If it does exist, we have a collision. If we have retried less than, let's say, 3 times, we regenerate and try again. If we have exceeded our retry limit, we fall back to a pre-generated key pool. Now let's talk about database selection. There is a critical architecture decision that affects performance, scalability, and operational complexity. Relational databases have several advantages. They provide asset transactions for consistency, ensuring our data is always in a valid state. They have mature tooling and operational practices built up for decades. They offer strong indexing capabilities for various query patterns, and SQL is a familiar query language for most engineers. However, relational databases also have few disadvantages. Horizontal scaling requires sharding, which adds a lot of complexity. Schema changes can be complex and require migrations. Join operations become pretty expensive at scale, and without proper configuration, they can be a single point of failure. NoSQL databases offer different trade-offs. They are built for horizontal scaling from the ground up. They have flexible schemas that can evolve easily, but they are typically eventually consistent by default, which may not be acceptable for all use cases. And they may also lack secondary index support, limiting the query flexibility. The key insight here is that there is no universally correct answer. The choice depends on our specific requirements, team expertise, and operational capabilities. Let's talk about how to decide between a SQL and NoSQL database for a URL shortener. For data model fit, URL mapping is essentially a key value pair. We don't have complex relationships that would benefit from relational joins. Our access pattern is almost entirely single key lookups. The pattern naturally fits in NoSQL, but SQL works fine too. For consistency requirements, the redirect must return the correct URL every time. A redirect to the wrong destination would be a serious bug. Eventual consistency may cause issues if a newly created URL is not immediately readable. Strong consistency should be preferred for writes. For operational considerations, we should factor in team expertise with specific database technologies. We should consider managed service availability in our cloud provider. We need to evaluate backup and recover capabilities. And we need to understand the cost at our projected scale. The flow works like this. We ask whether our data model has complex relations. If yes, SQL is probably the better choice. If no, we ask whether the strong consistency is critical. If strong consistency is critical, SQL with sharding works well. If eventual consistency is acceptable, NoSQL is a good fit. Let's talk about sharding. As our data grows beyond what a single database can handle, we need to distribute it across multiple servers. So why is sharding needed? A single database cannot hold all our data as we scale to billions of URLs. Write throughput has an upper limit per server. Read replicas only help with read traffic, not writes. And geographic distribution for low latency requires data in multiple locations. For sharding key selection, the short URL hash is a natural choice. It distributes data evenly across shards because hash functions produce uniform distributions. It enables direct shard routing because we can compute the shard from the short URL without any lookups. And it avoids scattered queries because all of the data of a single URL will be on one shard. For shard management, we need to plan for shard splits as the data grows. We should use consistent hashing for flexibility in adding and removing shards. We need to maintain a shard map in our configuration. And we should also automate rebalancing procedures to minimize the operational burden. The flow works like this. A short URL like ABC123 goes through a hash function. The hash function routes it to a shard router. The shard router redirects it to the appropriate shard, whether that's shard 1, shard 2, or shard 3. Let's talk about consistent hashing. This technique minimizes data movement when we add or remove servers from a cluster. The basic concept is that we map both keys and servers to positions on a ring. A key is assigned to the next server encountered when moving clockwise around the ring. When we add a server, it only takes keys from its clockwise neighbor. When we remove a server, keys only moves to this clockwise neighbor. This minimizes the amount of data that needs to move. Virtual nodes improve the distribution. Each physical server has multiple positions on the ring. This improves distribution uniformity because servers are more evenly spread around the ring. It allows weighted capacity assignment where more powerful servers can have more virtual nodes. And it provides smoother rebalancing when the servers are added or removed. For implementation details, we need to use a hash function with good distribution properties. We store the ring structure in memory for fast lookups. We update the ring when the topology changes, and we need to handle concurrent ring modifications carefully. The key insight here is that consistent hashing solves the rebalancing problem. With traditional or modulo based hashing, adding a server causes most keys to move. With consistent hashing, only a fraction of keys move. Let's talk about replication. Replication provides both durability and read scaling. In the primary replica mode model, all writes go to the primary server. Replica receives updates asynchronously from the primary. Read requests can go to any replica, distributing the load. If the primary fails, a replica can be promoted to take over. For replication factor, we should have a minimum of 3 replicas for durability. This protects against multiple simultaneous failures. We should distribute replicas geographically for disaster recovery. We need to balance durability requirements against cost, and we should consider whether we need replicas for read scaling. For consistency trade-offs, asynchronous replication increases write latency because we wait for replicas to confirm. Asynchronous replication risks data loss if the primary fails before the replication completes. Quorum writes, where we wait for majority of replicas, balances both concerns. And if we need read your writes latency consistency, we may need to route reads to the primary or use session affinity. The flow works like this. A write goes to the primary asynchronously replicates to replica 1 and 2. Reads can go to either of the replica, and if the primary fails, we can fail over to one of the replicas. Let's talk about caching. Given a read-heavy workload, caching is absolutely critical for performance and cost. So why is caching important? The redirect operation is extremely latency sensitive. Users expect links to work instantly. Most URLs follow a power law distribution where a small percentage of URLs receive the majority of clicks. A small cache can cover a large percentage of traffic that way, and our database simply cannot handle all the redirect traffic at scale. For cache placement, we should use application level cache in memory for hottest data. We should use a distributed cache like Redis for broader coverage. We should use a CDN for geographic distribution and edge caching. And we should leverage browser cache via response headers for repeated visitors. For cache sizing, we estimate our hot data working set. We target the 90% of highest cache hit ratio, and we monitor actual hit ratio in production and adjust. And we should size our cache based on observed metrics, not just estimates. The flow works like this. A request comes in, we check the CDN edge cache first. If that's a miss, we check the application memory cache. If that's a miss, we will check Redis. And if that's also a miss, only then we'll finally go to the database. And when we get a result from the database, we populate the caches for future requests. Let's talk about cache population strategies. There are 3 main patterns, each with different trade-offs. The cache aside pattern is the most common. The application checks the cache first. On a miss, it reads from a database. After reading from the database, it populates the cache. The application is responsible for managing both the cache and the database. This gives us the flexibility but requires careful implementation. The write-through pattern writes through both the cache and the database together. The cache always has the latest data because it's updated on every write. The downside is higher write latency because we wait for both writes to be complete. But consistency is simpler because the cache is never stale. The write behind pattern writes to the cache immediately and writes to the database asynchronously later. This provides the lowest write latency because we return as soon as the cache is updated. But there is a risk of data loss if the cache fails before the database write completes. The key insight here is that cache aside is the safest default choice for most applications. Write through is good when we need strong consistency. Write behind is only appropriate when we can tolerate some data loss for better performance. Now let's talk about cache invalidation. This is famously one of the 2 hard problems in computer science. For time-based expiration, we set a TTL on cache entries. Entries automatically expire after a set time. We balance freshness against a hit ratio. Longer TTL means better hit ratio but potentially stale data. We use longer TTL for stable data that rarely changes. And we use shorter TTL for frequently updated data. For event-based invalidation, we invalidate the cache when the URL is updated or deleted. We publish invalidation events to a message bus. All cache nodes subscribe to these events and evict the relevant keys. This handles distributed caches correctly but adds complexity. There are challenges at scale. Thundering herd occurs when a popular key expires and hundreds of requests simultaneously try to rebuild it. Caching stampede during invalidation has similar effects. There is stale data during propagation delay when invalidation events haven't reached all nodes. And coordinating invalidation across geographical regions add latency as well. The flow works like this. When data changes, we ask how frequently this type of data updates. If it's rare, we use TTL-based expiration. If it's frequent, we use event-based invalidation, publishing invalidation events so that the all node can evict this key. Let's talk about redirect status codes. The choice between 301 and 302 has significant implications. 301 permanent redirect tells browsers to cache the redirect permanently. The browser remembers the destination and goes there directly next time without hitting our server. This reduces server load significantly, but we cannot track clicks accurately because many clicks bypass the server entirely, and it's difficult to change the destination later because browsers have cached the old destination. A 302 temporary redirect tells browsers not to cache by default. Every click hits our server. This enables accurate click tracking because we can see every request, and it allows destination changes because browsers always check with us first. For our decision framework, we should use 302 if analytics are important because we need to see every click. We should use 301 for maximum performance when we do not need analytics. We can consider a hybrid approach where some URLs use 301 and others use 302 based on their type, and we should document this behavior for our users so they can understand the trade-offs. The key insight here is that this is a fundamental trade-off between performance and observability. We cannot have both preferred analytics and maximum browser caching. Let's talk about load balancing. The load balancer is the entry point to our system and it distributes traffic across our servers. Load balancers serve several functions. They distribute traffic across multiple servers to prevent any single server from being overwhelmed. They perform health checks and remove unhealthy nodes from rotation. They can handle SSL termination at the edge, offloading that work from application servers, and they can do geographic routing to send users to the nearest region. For algorithm selection, route robin works well when requests are uniform and servers have equal capacity. Least connections is better when requests have varying load because it sends traffic to the least busy server. Consistent hashing provides cache affinity, ensuring the same URLs always go to the same servers, which improves the cache hit rates. Weighted distribution allows us to spend more traffic to more powerful servers. For high availability, we should have an active passive load balancer pair so we have a backup if their primary fails. We need DNS failover between regions for geographic redundancy. We should implement health checks at multiple health levels, checking not just that the servers are responding, but that they are actually healthy. And we should also automate failover procedures to minimize the downtime. The flow shows that the clients connecting to a load balancer, which health checks and distribute traffic to multiple servers, all connecting to our backend services. Let's talk about rate limiting. Rate limiting protects our system from abuse and ensures fair usage. So why do we need rate limiting? It prevents abuse and spam by stopping malicious actors from creating millions of URLs. It protects our backend from overload during traffic spikes. It ensures fair usage across users so no one user can impact everyone else. And it helps control the infrastructure cost by limiting how much any single user can consume. For rate limiting dimensions, we should limit per IP address for anonymous users. We should limit per API key for authenticated users, typically with higher limits. And we should have per endpoint limits since some endpoints are more expensive than others. And we should also have a global limit as a safety net. For implementation approaches, the token bucket algorithm is popular. Tokens are added to the bucket at a fixed rate. Each request consumes a token. If no tokens are available, the request is rejected. Sliding window counters are an alternative that tracks requests in a moving time window. We should use a distributed counter and Redis to coordinate rate limits across multiple servers. And we should return HTTP 429 status with a retry after header to tell clients when they can try again. The flow works like this. A request comes in, we check if the tokens are available. If yes, we consume a token and process the request. If no, we return a 429 too many requests to HTTP response. Meanwhile, tokens are being refilled at a steady rate. Let's talk about analytics architecture. Analytics should be separated from the critical redirect path. For data collection, we log redirect events asynchronously so we don't slow down redirects. Each event includes a timestamp and short URL. We capture IP address and user agent for geographic and device analytics, and we can add geographic information through IP geolocation. For the processing pipeline, we stream events to a message queue like Kafka. Consuming processes aggregate events in time windows, and then aggregated results are stored in an analytics database. Raw events then go to the data lake for deeper analysis later. For query patterns, we need to support click counts per URL for user dashboards. We need time series of traffic to show trends over time. We need geographic distribution to show where clicks are coming from. And we need referrer and device breakdown for marketing analytics. The flow works like this. A redirect event is captured, it goes to a message queue, a stream processor consumes it, an aggregator computes summaries, aggregates, then it goes to a time series database for fast queries. And raw events, then they go to the data lake for deep analysis. Analytics storage. We need different storage systems for different analytics use cases. For real counters, we increment counters on each click using Redis for atomic increments. Redis is perfect for this because increments are fast and atomic. We periodically flush these counters to persistent storage to prevent data loss, and we accept minor inaccuracy for speed because analytics don't need to be perfectly precise. For time series data, we store click counts per time bucket, such as per minute or per hour. Time series databases are efficient for range queries like showing clicks over the past 30 days. They have built-in downsampling to automatically aggregate older data into coercive granularity, and they support retention policies for automatically deleting the old data. For separation from the core service, analytics failure should not break redirects. If our analytics pipeline goes down, links should still work. We use separate databases and services for analytics. Async processing decouples analytics latency from redirect latency, and we can scale analytics independently based on its specific needs. The flow works like this. A click event goes to Redis for real-time counter increments. Periodically, we flush these counters to persistent storage. Separately, the raw click event goes to an event log which feeds into the data lake for deep analysis. Let's talk about security. URL shorteners can be abused to hide malicious destinations, so we need multiple layers of protection. For malicious URL prevention, we should check URLs against known blocklist or malicious domains. We should integrate with safe browsing APIs like Google Safe Browsing to detect phishing and malware. We should scan for phishing patterns in URLs, and we should allow users to report abuse so we can investigate suspicious links. For input validation, we should validate URL formats strictly, rejecting malformed URLs. We should limit URL length to prevent abuse through successive long URLs. We should sanitize custom aliases to prevent injection attacks as well, and we should reject private IP addresses to prevent server-side request forgery. For access control, we should authenticate API users to track who is creating URLs. We should authorize the URL management operations so users can only modify their own URLs. We should rate limit by authentication level, giving authenticated users higher limits, and we should audit log all the modifications for security investigations. The flow works like this. URL input comes in, we validate the format, we check against the block list, we call the safe browsing API. If the URL is safe, we create it. If it's flagged as unsafe, reject it. Let's talk about abuse prevention beyond just malicious URLs. For spam detection, we monitor URL creation velocity to detect bulk creation patterns. We flag suspicious domains that appear frequently in spam, and we implement CAPTCHA for anonymous users to prevent automated abuse. For link rot prevention, we should validate destination URLs periodically to check if they are still working. We can notify URL owners when their links are broken. We might consider automatic expiration for URLs that have not been clicked in a long time, and we should provide broken link reports for users to review. For legal compliance, we need DMCA takedown procedures to handle copyright complaints. We may need geographic content restrictions for certain types of content. We need data retention policies that comply with regulations like GDPR, and we need to handle user data deletion requests within the required timeframes. The flow works like this. A URL creation request comes in, we check if the creation velocity is suspiciously high. If yes, we flag it for review. If no, we check if the domain is suspicious. If it's suspicious, we flag for review. If it's clean, we allow the creation. Flagged requests may trigger CAPTCHA or outright blocking. Let's talk about custom aliases. Many users want to choose their own short URL rather than accepting a random one. For validation rules, we should typically restrict to alphanumeric characters only. We need minimum and maximum length constraints. We should block reserved words and system paths to prevent confusion, and we need to decide on the case sensitivity. Most systems treat aliases as case sensitive to avoid user confusion. For collision handling, we check the availability before the creation. If the alias is taken, we return a clear error message. We can optionally suggest alternatives if the requested alias is unavailable. And we We should have a reserve system prefixes like API or admin to prevent conflicts. For premium features, we might restrict custom alias to paid users as a monetization strategy, and we can support vanity domains where users bring their own domain. We can offer brand protection reservations so companies can claim their brand names, and we can support transfer ownership for URLs that need to change hands. The flow works like this. A custom alias request comes in, we validate the format, we check for reserved words, we check if it's available. If it's available, we create the mapping. If it's not available, we return an error. Let's talk about URL expiration. Many use cases require URLs that automatically become invalid after a certain time. For expiration mechanisms, we store the expiration timestamp in a database alongside the URL mapping. We check expiration on every redirect request. If a URL has expired, we return the HTTP 410 gone rather than the redirecting. A background cleanup job eventually deletes the expired records. For cleanup strategy, a background job scans for expired URLs periodically. We delete in batches to avoid creating load spikes on our database. We might reclaim short URLs after a grace period, making them available for reuse. And we should always re-archive data before permanent deletion in case we need to recover it. For user experience, the expiration time should be clear in the API response when a URL is created, and we can send warnings before expiration via email for important URLs. We should offer an extension option so users can extend the active URLs, and we should have a grace period before recycling the short URLs to prevent confusion. The flow works like this. A URL with an expiration timestamp receives a redact request. We check if it's expired. If it's not expired, we redact normally. If it's expired, we return HTTP 410 gone. Meanwhile, a cleanup job periodically scans and deletes the old expired records. Let's talk about monitoring metrics. We need visibility into our system's health and performance. For availability metrics, we track uptime percentage per service. We track error rate by endpoint to identify problematic areas. We track failed redact percentage as a key business metric. And we monitor database connection health as well. For performance metrics, we track redirect latency percentiles, especially the 99th percentile. We track URL creation latency, and we track the cache hit ratio because drops indicate problems. And we also track database query times to identify slow queries. For business metrics, we track URLs created per time period to understand the growth. We track the redirects served per time period to understand the usage, and we track the active user count to understand the engagement. And we also track storage utilization trends for capacity planning. The hierarchy works like this. The system metrics fall into three categories. Available metrics include the uptime percentage and error rate. Performance metrics include the P99 latency and cache hit ratio. Business metrics include the URL created and the redirects served. The alerting strategy. Metrics are only useful if we act on them. For critical alerts, we should page immediately when a service is down or unreachable. We should page when error rate exceeds the threshold. We should page on latency SLA breaches. And we should page on database replication lag because that indicates potential data loss. For warning alerts, we should notify when the cache ratio is dropping because that indicates the problem is building. We should warn when the storage is approaching capacity. We should also warn on traffic spikes above normal levels, and we should warn when the certificates are approaching expiration. For alert management, we should route alerts to the appropriate on-call engineer. We need defined escalation procedures for when alerts are not acknowledged, and we should have runbooks for common issues so on-call engineers know how to respond. And we should conduct post-incident reviews to improve our processes. The flow works like this. A metric crosses the threshold, we determine the severity. If critical, we page on-call immediately and direct them to a runbook. If warning, we send a Slack alert and quick queue a ticket for review next business day. Let's talk about geographic distribution. For global services, we need to deploy in multiple regions to reduce latency. For multi-region architecture, we deploy services in multiple regions around the world. We route users to the nearest region for lowest latency. We replicate data across regions for availability, and we handle region failover when one region has problems. For data consistency challenges, cross-region replication has inherent latency due to the speed of flight. We need conflict resolution strategies if the same URL could be created in multiple regions simultaneously. Read or write guarantee may require routing users to a specific region, and eventual consistent replication is often acceptable for this use case. For traffic routing, we can use DNS-based geographic routing to direct users to nearby regions. Anycast provides automatic routing at the network level CDNs provide edge caching in many locations, and latency-based load balancing can route based on actual measured latency. The flow works like this. A user makes a request, GeoDNS determines the location, US users go to the US region, EU users go to the EU region, and the regions replicate data between each other asynchronously. Let's talk about the CDN integration. CDN caches are redirects at edge locations around the world. CDN benefits include caching redirects at edge locations close to users. This reduces latency for global users dramatically. CDNs can absorb traffic spikes because they have massive capacity, and most CDNs include DDoS protection as part of the service. For cache configuration, we need to set the appropriate cache headers to control the CDN behavior, and we should configure TTL based on the URL type, longer for permanent URLs and shorter for temporary ones. We need a strategy for cache invalidation when the URLs change, and we should monitor cache ratio to ensure that the CDN is providing value. There are some limitations to consider. Analytics accuracy is affected because our cache requests don't hit our servers. Cache invalidation has inherent delay across global edge locations, and costs can be significant at higher traffic volumes. And configuration complexity increases as we add more and more CDN rules. The flow works like this. A user request goes to the CDN edge location. If it's a cache hit, the CDN responds directly without hitting a service. If it's a cache miss, the CDN forwards to our origin server. The origin response includes the cache headers that the CDN uses to cache the response for the future request. API Gateway. An API gateway provides a single entry point for all your API requests. Gateway functions include serving as a single entry point for all APIs, simplifying client configuration. The gateway handles authentication and authorization centrally. It enforces the rate limiting across all services, and it can transform requests between different formats. Benefits include the centralized security policies applied consistently across all services. We get unified logging and monitoring in one place. The gateway can handle protocol translation if needed and simplifies the API versioning management. For implementation options, cloud providers offered managed gateway services that can handle scaling and operations. Open source options like Kong gives us more control but require more operational work. We can build a custom gateway for specific needs, as well as service mesh technologies provide gateway-like functionality at the infrastructure layer. The flow shows clients connecting to API gateway, which handles auth, rate limiting, and transformation before the forwarding to our URL service. Let's talk about the authentication methods. Different clients need different authentication approaches. So API key authentication is simple to implement and use. The key is included in the request header. Keys are easy to rotate and revoke when compromised. This approach is suitable for server-to-server communication where secrets can be kept secure. OAuth 2.0 is the industry standard protocol for user authentication. It supports multiple grant types for different scenarios. It enables code permissions so tokens can have limited access and is designed for third-party integration. For token management, we need secure token generation using cryptographically strong random numbers. Access tokens should be short-lived to limit the damage for compromised tokens. Refresh token rotation provides the additional security. And we also need revocation mechanisms for compromised tokens. The flow works like this. We determine the client type. For our server to server, we use API keys and headers. For user-facing application, we use OAuth 2.0 with short-lived access tokens and refresh token rotation. For the concurrency handling, with many servers handling requests simultaneously, we need to handle race conditions. For race conditions, multiple requests might try to claim the same custom alias simultaneously. Counter increments could collide but if not handled atomically. Cache and database can become inconsistent during concurrent updates, and concurrent URL updates could overwrite each other. For locking strategies, database unique constraint handles the custom alias rate condition at the database level. Distributed locks coordinate access to shared resources across the servers. Optimistic locking with version numbers detects the conflicts after the fact, and the pessimistic locking prevents the conflicts by locking before updates but reduces the concurrency. For idempotency, we should support the idempotency keys for URL creations so that the retire requests produce the same result. Operations should be retry safe so clients can safely retry on timeout, and we aim for exactly once semantics where possible. And we need proper client retry handling with exponential backoff. The flow works like this. Concurrent requests come in. We determine the conflict type. For same alias conflicts, database unique constraints handle it. For counter conflicts, we use atomic increments. For update conflicts, we use optimistic locking with version numbers, and on conflicts, we retry with a new key. Let's talk about the read path optimization. Since redirects are our most frequent operation, we need to optimize this path aggressively. For caching everything, we should cache in multiple layers. Application memory cache handles the hottest data with sub-millisecond latency. Distribute cache like Redis handles warm data, and CDN handles global distribution. For database optimization, we should have an index on the short URL primary key, and we should be clustered for fastest lookups. Read replicas scale our read capacity. Connection pooling prevents the connection overhead from dominating, and we should analyze and optimize slow queries. For response optimization, we should minimize response payload size. HTTP compression should be enabled. Keep alive connections, avoid connection setup overhead on every request, and we can pre-commute redirect responses to avoid any computation on the critical path. The flow works like this. A GET request for a short URL comes in. We check the local cache. If hit, we return instantly. If miss, we check Redis. If we hit there, we return. If we miss from Redis, we read from database replica, and then we populate the caches for future requests. Let's talk about the write path optimization. While reads dominate, we should still make writes as efficient as possible. For async processing, we can return to the client immediately after validation. The actual URL is queued for background processing. Analytics are handled asynchronously, and we can batch database writes for efficiency. For database optimization, connection pooling is critical to avoid connection overhead. We should batch inserts when possible, especially for bulk operations. We should use the appropriate escalation level, not higher than necessary, and we should schedule index maintenance during the low traffic periods. For backpressure handling, we need to monitor queue depth to detect buildup. We should reject requests when the system is overloaded rather than letting queues grow unbounded. Graceful degradation modes can disable the non-essential features under load, and autoscaling triggers should add the capacity when needed. The flow works like this. A post request comes in, we validate the input, we generate a key, we return to the client immediately. Meanwhile, the write is queued. A background process handles the async database and async analytics update. Let's talk about the hotkey problem. When a URL goes viral, it can overwhelm our caching infrastructure. The problem is that a viral URL might receive millions of requests per second. The single cache key becomes a bottleneck because all requests are hitting the same cache node. The database shard holding the URL can become overloaded as well. The result is that the service degradation for that URL and potentially others on the same shard. For mitigation strategies, we can replicate hotkeys across multiple cache nodes so requests can spread out. We can add a local application cache specifically for the hottest keys and request co-scaling groups, multiple requests for the same key into a single backend request. And the circuit breakers protect overloaded keys by failing fast rather than overwhelming the backend. For detection, we should monitor key access frequency to identify the hotkeys. We should alert on sudden traffic spikes to a single URL. We should track cache eviction patterns because hotkeys cause high eviction rates, and we should identify a hot shard that might be receiving disproportionate traffic. The flow shows a viral URL receiving a massive traffic here. The single cache key becomes a bottleneck. We have three solutions. Key replication spreads load across cache nodes. Local cache handles the hottest request, and the request co-scaling reduces the backend call. Let's talk about database indexing. Proper indices are essential for query performance. For the primary index, the short URL should be a primary key with a cluster index for faster lookups. B-tree structure is typical and works well for our access pattern. We should keep the key size small because smaller keys mean more keys per index page and faster traversal. For secondary indexes, we might index user ID for dashboard queries that list all URLs for a user. We should index expiration time for the cleanup job that finds expired URLs. We might index creation time for auditing queries as well, and we should consider the overhead each index adds to write operations. For index maintenance, we should monitor index fragmentation over time. We should rebuild indexes during low traffic period. We should analyze the query patterns to ensure indexes are being used effectively, and we should remove unused indexes because they slow down writes without providing benefit. The hierarchy shows primary index on a short URL using a clustered B tree and secondary indexes on a user ID, expiration time, and creation time for the respective queries. Talk about the deployment and testing. Safe deployment practices are essential for production systems. For deployment methods, rolling deployment gradually replaces old instances with new ones for zero downtime. Blue-green deployment maintains two complete environments for instant rollback. Canary deployment routes a small percentage of traffic to new code first, and feature flags allow us to control feature availability without deployment. For testing strategy, unit tests cover a URL validation logic and encoding. Integration tests verify the database operations work correctly, and the load tests identify the bottlenecks under the production-like traffic. And end-to-end tests they verify the complete redirect flow. For configuration management, we should maintain environment-specific configurations for development, staging, and production. Secrets management keeps the API keys and database passwords secure. And the feature flags integrates with our deployment for control our rollouts. And configuration versioning tracks changes over time as well. The flow shows the code going through unit tests, the integration tests, and the load tests, and then canary deployment. If the issues are detected, we can always roll back. If everything looks good, we can proceed to the full rollout. Let's talk about the failure scenarios. We need to plan for what happens when components fail. For cache failure, we fall back to the database. Latency will be higher without the cache. Database load will increase significantly. Circuit breakers should protect the database from being overwhelmed. For database failure, we fail over to a replica if the primary fails. Redirects can continue serving from the cache for URLs that are cached. New URL creation will be blocked until the database recovers. We need to alert and remediate quickly. For complete outage, we should serve a static error message so users know what's happening. We should update our status page to communicate with the users. Incident response procedures should be activated, and we should conduct a postmortem after the recovery to prevent for it happening again. The flow over here shows a component failure. We determine which component failed. Cache failure means we fall back to the database with high latency, but the system continues. Database failure means we serve from the cache and block new writes, but the system partially continues. Complete outage means we serve the error pages and activate the incident response. Let's talk about how to communicate effectively in a system design interview. Technical knowledge is important, but communication is pretty important as well. For clarifying requirements, we should ask about the scale expectations, how many URLs, for example, how many required redirects per day. We should confirm feature priorities as well. Is analytics important? Do we need custom aliases? We should understand constraints like budget, timeline, and existing infrastructure as well. And we should validate our assumptions explicitly rather than making silent assumptions. For structuring our answer, we should start with requirements get summary to confirm the understanding. Then we present the high-level design before diving into details. Then we deep dive on key components at one at a time, and throughout we discuss trade-offs with each decision. For managing time, we should allocate the time for each section and stick to it. We should not get stuck on one area while neglecting others, and we should cover breadth before depth to show that we understand the full system. And we should save time for questions at the end as well. The flow over here shows clarifying requirements, then high-level design, then deep diving into components, and then discussing trade-offs and then handling questions. We should allocate roughly 5 minutes for requirements, 10 minutes for design, and 15 minutes for deep dive and discussion. Let's talk about the cost optimization strategies. Building a system that works is one thing. Building a system that works economically at scale is another challenge. We should think about costs in 3 categories: infrastructure, storage, and operations. For infrastructure costs, the first strategy is right sizing our compute instances based on actual load patterns. Many teams over provision because they are worried about traffic spikes, but this wastes money during the normal operations. We should use reserve capacity for our baseline traffic because reserve instances typically cost 30 to 60% less than on-demand pricing. For batch jobs like analytic processing or cleanup tasks, spot instances can reduce costs by 70 to 90%. And for workloads that are infrequent or unpredictable, serverless options can be more economical because we can only pay for the actual usage. For storage costs, we should implement tiered storage. Hot data that's accessed frequently stays on fast, expensive storage. Cold data that is rarely accessed moves to the cheaper storage classes. And we should compress URL data wherever possible. Though we need to balance compression overhead against the latency requirements here as well. We should archive or delete expired URLs aggressively rather than letting them accumulate. And we should use an appropriate replication factor as well. 3 replicas might be necessary for critical data, but some auxiliary data might only need 2. For operational costs, CDN offload is significant. Every request served from CDN edge is a request that does not hit our origin servers. Caching reduces database load, which means we can use smaller databases instances. We should schedule batch analytics processing during off-peak hours when our compute is cheaper, and we should regularly audit our infrastructure to eliminate unused resources that are still incurring cost. The key insight here is that cost optimization should be an ongoing practice, not a one-time effort. Traffic patterns change and pricing models evolve, and our system grows. A regular viewing ensures that we are not overspending. Now let's talk about the extended features. Once you have a solid foundation, there are many directions we can take a URL shortener to provide more value. The first category is link management features. QR code generation is a natural extension since QR codes are essentially visual representations of URLs. Link preview cards with open graph metadata helps when URLs are shared on your social media. Branded custom domains allowing enterprise users to use their own domain instead of ours, which builds trust with their audience. Link grouping with campaign management helps marketing teams organize their URLs by campaigns or initiative. The second category is advanced analytics. Real-time clickstream visualization let users see clicks as they happen, which is valuable during product launches and marketing campaigns. Conversion tracking with pixel integration connects clicks to downstream actions like purchases or sign-ups. A/B testing with traffic splitting allows users to test different destinations and measures which performs better. And audience insights derived from geographic and device data helps users understand who is clicking their links. The third category is enterprise capabilities. Team workspaces with role-based access let organizations manage URLs collaboratively with appropriate permissions. Single sign-on integration connects with corporate identity providers. Audit logs track all changes for compliance requirements and industries. And SLA guarantees with dedicated infrastructure provide the reliability that enterprise customers require. The key insight here is that these features represent the different monetization tiers. Basic link shortening might be free, but advanced analytics could be a mid-tier offering, and enterprise capabilities command premium pricing. This is how URL services typically structure their business model. Now let's talk about data migration strategies. As the system grows and requirements change, we will need to evolve our database schema without taking the system offline. For schema evolution, we should use backward compatible changes wherever possible. This means adding new columns as nullable before making them required. During migration periods, we might need to dual write to both old and new schemas, and feature flags let us control which code paths use a new schema, allowing gradual rollout. For zero downtime migration, the process should follow a careful sequence. First, we create a shadow table with the new schema alongside the existing table. Second, we implement dual writes so all new data goes to both tables. Third, we backfill historical data from the old table to the new table. Fourth, we verify with checksums that all data has been migrated correctly. Fifth, we switch traffic to read from the new table. And finally, after a verification period, we deprecate and eventually drop the old table. For data integrity, checksums are essential to verify migration completeness. We should run reconciliation jobs to detect any discrepancies between old and new data. We need to maintain an audit trail for all migrations and debugging and compliance. And we should keep the original data accessible during the verification period so we can roll back if issues are discovered. The key insight here is that migration should be boring. The more exciting a migration is, the more likely something has gone wrong. Careful planning and incremental steps minimize risk, and we should always have a rollback plan, and we should test that rollback plan before starting the migration. Now let's talk about common interview pitfalls. Understanding what not to do is just as valuable as knowing what to do. The first category is requirement pitfalls. The most common mistake is jumping straight to a solution without clarifying scale. A system for 1,000 users looks completely different from a system for 100 million users. Another mistake is over-engineering for requirements that were never stated. If the interviewer did not mention about global distribution, you should not be spending 10 minutes designing a multi-region architecture. Conversely, ignoring non-functional requirements entirely is also problematic. Latency, availability, and consistency requirements drive major architectural decisions, and making assumptions without stating them explicitly leaves the interviewer guessing without our reasoning. The second category is design pitfalls. Choosing a database without justifying the trade-offs signals shallow understanding. We should explain why we chose SQL over NoSQL or vice versa. Underestimating the importance of caching is another common issue. For read-heavy workloads like URL shorteners, caching is not optional. Ignoring failure modes and edge cases suggests that we only thought about the heavy path, and designing for average load instead of peak load means our system will fail exactly when it's needed the most. The third category is communication pitfalls. Monologuing for 10 minutes without checking if the interviewer is following along loses alignment. We should pause periodically and ask if they have questions or want us to go deeper on anything. Getting defensive when challenged on decisions makes looks inflexible. Interviewers push back to generally see how we think, not because they think we are wrong, but it's just that they want to understand our decision, like our thought process. Spending too long on one component while neglecting others show that poor time management, and not drawing diagrams during clarify architecture forces the interviewer to build a mental model from words alone, which is pretty difficult for them. The key insight here is that system design interviews test communication and structural thinking as much as technical knowledge. A candidate who communicates clearly with moderate technical depth will often outperform a candidate with deep technical knowledge who cannot explain their reasoning. These are the key numbers and decisions to remember for your URL shortener design system. So, for key numbers to remember, a 7 character base62 string uses 3.53 trillion possible combinations, which should be sufficient for most scale requirements. You should be targeting availability of 99.9%, which is translates to approximately 8 hours of downtime per year. The read to write ratio for URL shortener should typically be between 100 to 1 or higher, which should be driving our caching strategy. And our cache ratio should be 90% or higher to keep our database load manageable. For critical design decisions, URL generation should use a counter-based approach with base62 encoding for guaranteed uniqueness without the collision checks. For database selection, NoSQL works well for this simple key value access pattern at scale, though SQL with sharding is also a possible option. Caching should be multi-layer with CDN at the edge, Redis for distributed caching, and local application cache for the hottest keys. And redirect status code should be 302 if we need analytics or 301 if we prioritize performance and browser caching. For production checklist, rate limiting should be implemented on all public endpoints to prevent abuse. Monitoring dashboard should be configured with alerting for key metrics like latency, error rate, and cache ratio. A runbook should be documented for common failure scenarios so on-call engineers know how to respond. And the system should be load tested to at least 2x the expected peak traffic to ensure we have headroom for unexpected spikes. The key insight from this entire deep dive is that the URL shortener design touches on every fundamental distributed system concept. Mastering this design demonstrates the competence across API design, database selection, caching strategies, scaling techniques, and operational excellence. If you can design a production grade URL shortener, we have the foundation to tackle most of the system design problems. Let's wrap up with the key takeaways from this deep dive. For architecture essentials, the RAID-heavy workload should drive our caching strategies. Caching is not optional for URL shortener at this scale. Key generation is a critical design decision that affects the uniqueness guarantees and system complexity. Sharding enables the horizontal scaling when a single database is not enough, and geographic distribution reduces the latency for global users. For production requirements, monitoring and alerting is pretty important. We cannot operate a production system without both of these things. We should plan for failure from the start, designing graceful degradation into the system from the get-go. Security and abuse prevention matters because URL shorteners are attractive targets for malicious actors, and cost optimization requires ongoing attention as the status scales. For interview success, we should clarify requirements before diving into the design, and we should justify every major decision with reasoning. We should discuss trade-offs proactively rather than waiting to be asked, and we should communicate clearly throughout explaining our thought process. The key insight is that a URL shortener looks pretty simple but touches on almost every fundamental distributed systems concept. Mastering this design demonstrates competence across caching, databases, scaling, and operational excellence. Thank you for watching, and if you have any questions, please let me know. Thanks.